My name is Gary Pocock and this is my Week 8 reflection for the Physics Modelling Instruction course. This week I'm just going to have a close look at the Lab 1 and Worksheet 1 for the Circuits unit. I found this lab quite challenging and I was thinking could I present this to my students in a way that was logical and clear. So this reflection is going to be partly me trying to think of preparation material for my students and also raising some questions about some aspects of the lab. Okay, so to start off, I was thinking, well, what would I say to my students in preparation for this lab? And I'd remind them that the fundamental conclusion we've got from Unit 2 is that the motion of charged particles is caused by an electric field. So we're now going to look at charged particles moving in circuits, and we will be constantly looking to explain that motion in terms of a field in the circuit. Alright, and then I'd also remind them that, or tell them that measuring an electric field is difficult to do, and we have to infer the existence of an electric field indirectly by measuring changes in electric potential. Alright, so that's the first step. But then when I was looking at the lab and looking at the diagram, sorry, that's not the lab, looking at the diagram, get there in a minute, I thought this could be quite challenging for students just to be given a capacitor and some wires and to ask them to think about potentials in these wires. So I thought what I would do is, just as preparation, give them a schematic diagram. So I started off with something like this. And so here are my two parallel plates and here are my wires in the circuit. And well, here I might just simply asking the same question that's in the lab. What would you expect the potential difference to be between the various points on this schematic diagram? I think that would not be too difficult for the students to answer when it's presented to them like that, and then I could cross over, well, not quite yet, but eventually cross over to the actual diagram of the capacitor, and hopefully the students will see the parallels between this schematic diagram and the capacitor and the wires. But of course this diagram is not exactly like the capacitor and the wires, because in that situation, sorry, skipping ahead a bit, in that situation the wires are on the outside, so we'll have to build up to that situation. But let me just go back to my very simple setup here with the wires between the two plates, and that now raised the question of what would the field look like for this arrangement. Now I wouldn't be just expecting the students to do this, but hopefully the question would give them pause, because this is a complex charge arrangement. What we've got is two parallel plates. We know that there is a uniform field between two parallel plates, but we've also got two wires, and wires are cylinders, thin cylinders, so they would have a radial field, something like that. So who knows what the combined field would look like? It's not at all obvious. So what I did was I went into the eField software and had a go at approximating it. Alright, so here's what I've done. So I've assumed that the parallel plates, now I'm fully aware that this is not parallel plates here. These are cylindrical rods. So I'm hoping that this will still give a reasonable approximation of the field for a parallel plate, but I'm not 100% sure. Anyway, so here I've got it. I've put a high charge on the two plates, and then to model the thin wires, I've put a low charge on the thin wires and looked at the combined field. And what it seems to be telling me is that the field here in the middle between the two wires is actually quite low compared to the field outside. Here we see the almost uniform field, but the radial nature of the wires is pushing up these lines here. And again, for some reason, which I don't have a clear explanation for, the field seems to be weakest in between the wires. So for me, that raises a question mark about something that's said in the lab, because if we look up the top here, it's stated that yes, we are going to be measuring potential as an indication of field strength, and field strength is proportional to the difference in potential. Okay, well, I know that's true for parallel plates, but my question is that really true for other complex arrangements of charges? And this particular arrangement is suggesting to me that that may not be the case, because we'll have we know that the potential difference between these two plates is the same as the potential difference between the ends of the two wires, and yet clearly the field up here field strength is different to the field strength down here. So I just have a question mark about that. Alright, so moving on. So now we've got the wires on the outside, which more closely fits the actual lab situation with our capacitor and our wires. And I ask the same questions. What will the voltmeter read? Hopefully it should be reasonably clear that the answers will be exactly the same as the previous arrangement. And again, I ask, what about the field lines? Well, this looks even more complex than before. So once again, I've had a go at constructing it in the eField software. And again, we see there is a distinct lowering of the field strength between the wires in comparison to the field strength between my plates, well, lines of charge. And in this case, we see that the fringe field of the plates is having an effect on the field between the two wires. And fringe fields are not mentioned at all in these notes. So, and I understand that that's a complication that obviously the authors have decided to sidestep, but it just worries me a little that students may need to be aware that when you've got parallel plates, the field is not just between the plates, it's on the outside as well, and that's actually quite important for explaining how fields are created in circuits. Okay, so that's just my question mark over the way that this lab is constructed. Alright, so that's just my conclusion so far, that the field due to parallel plates has a significant influence on the net field between the wires, and that's true even when the wires are not lying between the two plates, because there is a significant fringe field around the parallel plates. And my query is it really true that the field is proportional to the potential no matter what configuration we have for the charges? And my diagrams seem to suggest that that is not the case. So, for example, the answer to this question here in worksheet 1, where we are asked to sketch the electric field strength. So the question was down here, so here we have our diagram, and we've got our two fields, and notice how they're drawing parallel lines between C and D here. I think that's what worries me. I think that's a little bit misleading. I understand why they've drawn the wires so fat, so we've got room to draw the charges and everything, but there's a danger here that we can mistake this C and D for a pair of parallel plates, whereas in fact they're not. It's a very thin point at C and D, so the field is unlikely to be parallel. And as my diagrams are suggesting, I have doubts about whether the electric field strength between A and B and C and D are exactly the same. Anyway, moving on. Of course, what really matters is the field inside the wires. Oh, and I would mention to students that all my diagrams, this would be a good point to mention that the charge is sitting on the surface, and this is what's indicated in my diagrams. It's easy for me to forget that, and this would look rather odd to students, having seen all these plus and minus signs sitting around the outside of the charge of the wires. So I think it would be very important to explain to students why the diagrams look like that. All right, back to the point. It's the field inside the wires that is going to determine how the charges move. So, obvious question, when C and D are not in contact, what is the field in the wires? Students should answer that the net field must be 0 because the charges are not experiencing any movement whatsoever. And then the follow-up question, well, what must the field be in order for the charges to move? So obviously you have to have a non-zero net field in order for the charges to move. Okay, finally, after all these preliminaries, we can ask the obvious question, what happens if we touch point C and point D? I think it's very intuitive that the charges are going to flow through the wire and neutralize, and I don't think students would have any problems accepting that. The challenge is to explain that in terms of the creation of a field, and this is where we get to the interesting point in the lab, where, oh sorry, it's not the diagrams in the teacher notes, where the transient potential is mentioned, and it's explained how that transient potential is set up in this diagram here. It's a very challenging diagram, and for my last point I thought I'd try and supplement that with another diagram of my own. So what I've got here is, I said, let's forget about the plates for the moment. I've just got a positively charged rod and a negatively charged rod, initially separate, so there is a potential difference between them, and then they are joined together. What's going to happen? Well, there's a potential difference here clearly at the point in which they come into contact. So in the very first movement is going to be negative charge on this side, moving over to the other side and neutralizing the positive charge over there. So that will leave a little neutral gap here. And now we see there's going to be a difference in potential between the outer end of the rod and the inner end. This is going to be true on both sides. And this is what's going to create the transient potential difference. And then I thought, okay, I'll just keep following that through, and then we slowly see the charges moving towards the center because of this field that's set up, and gradually neutralizing each other.